Welcome everyone to West Explains Best. Today we're going to be talking about rational exponents. So let's go ahead and get started. Some of the basics of what a rational exponent is we need to understand what a radical is first. So as we look at a radical, we can break it down into basically three components. So the first thing you have is you have the radical. So let's go ahead and write radical here. I'm going to color match it. So we're going to write radical in red. This is the radical, the little symbol that kind of looks like a check mark. Now, important thing about radical is a radical indicates kind of the opposite of exponents or raising numbers to a power. So this indicates, and we're going to talk about it in a second, this is the index. So this little n there, that number, this indicates some sort of number that goes there, and we'll talk about what that means. Then we have the number underneath the radical, and we call this the radicand. So anytime you hear about the radicand, that is the number underneath the radical, or term underneath the radical. Could be a variable. So let's talk about something that we're more familiar with. We're talking about squares and perfect squares and square roots. Most of us know that the square root of 4 equals 2, the square root of 9 equals 3, the square root of 16 equals 4, and so on. What does that mean? Well, all this is talking about is what number times itself twice equals 4. Let me change this a little bit smaller. And that's why this is 2. What number times itself twice is 9, and that's 3. 3 times 3 equals 9. One number times itself twice equals 16, and that's 4. So what number times itself twice equals 25. Now, how do I know it's twice? Well, a square root is written like this, and it's an implied that there is a 2 there, but you don't write the 2 because it's like the basics of radicals is the square root. So it's implied that there's a 2 there, but it's not written like ever. So if you see it written, that's more the exception than the rule. So what number times itself twice? 2 times equals 25. That's what a square root is. Now let's go to a different radical. We still have the radical, the check mark. Okay, as you can see here, we still have the check mark, but now we have a different number there. Instead of no number, and no number means 2. So if we have this, it's equal to this. Okay, it's the same thing. But now we have a 3. So what does that mean? It means what number multiplied by itself 3 times, let's use blue, 3 times equals 8. That's what the index indicates. It indicates how many times the number needs to get multiplied by itself to equal inside the radicand, or to equal the radicand. So let's go over a couple examples just so we can solidify this understanding. So here we have the cubed root of 125. What number times itself 3 times equals 125? If you're unfamiliar, one thing you can do is you can use a factor tree and divide by prime numbers. So if we divide this by 5, which is a prime number, we get 25. Divide by 5, and we get 5. Now, hopefully you can see something here. You can see that number 1, the index is 3. And number 2, we have 3 numbers times itself to get the number underneath the radical, okay? So if we were to rewrite this, we could write this 125 as 5 times 5 times 5. Well, what number times itself 3 times equals 125? Clearly the answer is 5. So that's one way to look at this problem, is to understand that we can use a factor tree, factor this thing out, and see how many times we get a certain number times itself to equal the number underneath the radical. We can do the same thing with 16. So now we have a different problem. We have the 4th root of 16. So what number times itself 4 times something times something times something times something equals 16? So what is that number? Well, we can factor tree again. So we're going to get this going. One thing we can divide by is 2. That's a prime number. We can divide by 2 again. We get 4. We divide by 2 again. We get 2. Let me change the color of this. I'm going to change it to red. Style. Let's make it red. Okay. The reason why is I want to use this highlighter. Okay. So now we can see we have 2 times 2 times 2 times 2. We could rewrite this problem as the fourth root of 2 times 2 times 2 times 2. So what times itself 4 times equals 16? 2 does. Okay. Now we don't write 2 times 2 times 2 times 2 because that gives us 16. We want to know what times itself 4 times equals 16. So our answer is 2. Finally, we have the cube root of 64. It's like the 125. We're thinking of a number times itself 3 times. That gives us 64. I like going to the factor tree right away. So let's go to the factor tree. We can divide by 2, and we get 32. We can divide by 2 again. We can get 16. We can divide by 2 again. We get 8. We divide by 2 again. We get 4. We divide by 2 again, and we get 2. Okay, now look here. It doesn't look like we have a number times itself 3 times. We have a number times itself 6 times, but not 3 times. So what can we do? Well, instead we could group it up. Okay, since there's 6, whoops, let me go ahead and highlight these again. Since there's 6, we could group these up into groups of 2. Okay, how many groups of 2 can I create? 3. Okay, so essentially, because we wanted to find something times itself 3 times, we wanted to divide it up into 3 groups, and it happened to be 3 groups of 2. Now, what does 2 times 2 equal? 2 times 2 equals 4. 2 times 2 equals 4. 2 times 2 equals 4. So instead of writing the cube root of 64 as 2 times 2 times 2 times 2 times 2 times 2, we could write it as the cube root of 4 times 4 times 4. Now it's easier to recognize what times itself 3 times equals 64. That is 4. So 4 is our answer in this case. We had to get a little creative to divide it up into 3 groups, as we showed in green, in order to find our answer. But it is possible. Now we're going to move on to a drastically different concept. It's related, but it's, for most people, this is kind of game-changing. So let's say we have a power here, a radical here, and we want to convert it into a power. How would we do that? Well, in order to rewrite it, a radical as a power, we use fractions like this. This kind of originated with computer programming and how computers can more easily read it, but the designated understanding and acceptance of how you rewrite radicals in exponent form is with fractions, okay? So notice how I put the index under 1 in the fraction. So I changed the index to be in the bottom of a fraction where 1 is in the numerator, okay? Now let's take the same concept, but expand it a little bit. Now let's take that same nth root of a, and now we're going to raise that to the n power. What do we do? Well, let me break it down first. We can rewrite inside the parenthesis as 1 over a to the n. Okay, so that's our first step. But now we still have to raise it to the n power. What do we do when we raise an exponent to a power? Is we multiply exponents. That's M-U-L-T, by the way. A little messy, but... So what does that become? When you multiply the powers, you get a to the m over n. And that is our notation there. So this is an important thing to understand, is the bottom number in a fraction and exponent indicates a radical or a root, where the top number is the power or the exponent. I'm just going to put power here because we're multiplying something times itself a certain number of times, and the root indicates what number times itself equals the base. So there's two considerations to make there. The easiest thing to do is kind of practice this, so we're going to go ahead and get started with that. So we're going to rewrite in exponential form. So what do we got going on here? Well, we have a root, we have a radical inside the parentheses, and then we're raising to a power. So the first thing we should identify is, what is our index of this radical? It doesn't look like there is anything, but there is. Remember, there's always an implied 2 there for a square root. So we know we can rewrite the parentheses here as x to the 1 over 2. That's the same thing as a square root. So anytime you have a square root, it's always going to be equal to 1 over 2 for the power. Now we're raising this to the third power. So we multiply exponents, so we get x to the 3 over 2. A quicker way to do this problem is to recognize that this is going to be the bottom because this is the index of root, and that goes in the bottom. And then we have a power, and that goes in the top. So we have index of root in the bottom. Oops, I wanted green to show you. Index of root. Okay, let's keep applying this concept. The more times we do it, the better we're going to get at it. So here we have our power. Here we have our index of our root. Let's use green to stay consistent. That's our index. Index should go in the bottom. Now, let's keep the base the same. So the base was 2. We're going to keep it 2. But now we're going to put the power in the top and the index in the bottom. So 7 over 3. And that can be our final answer. That is written in exponential form. Same thing here. We have our index here. This is going to be in the bottom. Let's keep our base the same. Let me just highlight our power here. Now, even though it's not in parentheses, this is still a power because it's y to the second power. And this is still an index because it is inside the little cubby of that little radical. So we're going to write y, that's our base. Our index goes in the bottom. Our power goes in the top. Whenever possible, you always want to reduce. So we want to reduce this into the most simplified form. So this equals y to the 1/2 power. Now, if you recognize y to the 1/2 is the same thing as square root of y, so these two are equivalent. One is just a little bit more reduced. So that's the power of rational exponents, is you can reduce these a little bit more easily. Let's move on to letter D. Here we have the square root of 4 to the -1. Again, let's highlight our index. Okay, it doesn't look like we have an index, but the index, there's an applied 2. And then let's highlight our power, which is -1. So we could write this in exponential form. What I was using blue. Let's stay consistent. 4, power goes in the top, index goes in the bottom, 4 to the -1/2. Now, as you recall, we could also write this as 1 over 4 to the 1/2. That's what you do with negative exponents to make them positive. Okay, just as we did before, we went from one to the other. Now we have to go from exponential form to radical form. So now we're going to be doing the same thing. We need to identify each piece. So here we see the index will go in the bottom. Power goes on the top. The base needs to stay the same. So the base, here's the base. So we have x, and we can raise it to the second power. And then we're going to take it to the cube root. There's my index. There's my power. And my base stays the same. Now, can I rewrite this as x cube root raised to the second power inside parentheses like that? Yes, it's the same thing. So these are equal, so either one is correct. I just like writing it like this because you avoid writing parentheses and make it a little bit more neat, in my opinion. Okay, now we have the next one. We have 3 times a to the 5 over 4 power. Index in the bottom, power top, and then the base stays the same. Now, here's the question. What is raised to the 5/4 power? Is it just a, or is it a and the 3? It is just the a. So only the a gets the power. The 3 does not. Now, if this was written like 3a, the 5/4, then the 3 would also get the power. But it's not written like that. So the 3 needs to stay alone outside. He does not get the power. We're going to write a radical with the 4 there because that's the index. And then a to the 5th, there's our answer. The 3 stays by itself. It does not get affected by the power. We're going to have the same thing here. So we have 6. Okay, index is in the bottom. Power is in the top. So we're going to, and the base stays the same. So y to the 3rd, 5th root of y to the third. So that's our index. And then we can leave it like that. That's fine. Let's go over to our last one. Okay, this is a counterexample to this one. See how these ones are different. Okay, these are not the same. And notice because it's the parentheses that it is so. So now we have two bases. Both of these are bases. And we're going to do both of these to this index for the radical and this power. So let's write our base. So we're write our base, and this is what's going to happen. I'm going to put it in parentheses still, just to be safe. I want to put it to the fifth power, and then I'm going to take the cube root of that. And that is my final answer. I hope this was enlightening. Hope you learned something about rational exponents. And until next time, be good, be kind, be true, be nice, and be honest.